Now, let's see. Example. That's the best way to make sense of anything, is to do examples. So in a table of reduction potentials, we have the following. We have let's see, should I write it out or should I, yeah, it's fine, I'll go ahead and draw the structure. H3CCH, this is acetaldehyde, plus 2H plus 2 electrons goes to, you know what, actually I'm going to make this a little bit easier. I'm not going to draw out the structures, I'm just going to go ahead and write out the words. I think that's better. So we have acetaldehyde plus 2H plus 2 electrons goes to ethanol, and its standard reduction potential happens to be minus 0.197 volts. Okay, well, we also have the following. We have something else in the table, and it says NAD plus H plus 2 electrons goes to NADH. Now, don't worry about what NAD plus and NADH are right now. We're actually going to be discussing that in the next lesson. For right now, it's just a species. It is the oxidized version of the species. In the vicinity of a couple of electrons, when it becomes reduced, it turns into this thing called NADH, and it has a reduction potential relative to the reference hydrogen electrode, and its reduction potential is the following. These are negative 0.320. Now, the question is, what happens when these species are brought into contact with each other? When I have some acetaldehyde, some ethanol, some NAD+, and some NADH, what's going to happen? Well, take a look at the reduction potentials. This is negative 0.197, and this is negative 0.320. This one is actually more positive than this one, so this will end up staying as written. The acetaldehyde will reduce to ethanol. This one will end up having to reverse. It's going to end up being the NADH that's going to end up turning into NAD+. Acetaldehyde will reduce. NADH will end up oxidizing. That's what's going to happen. So, what happens? Well, so the E of the acetaldehyde is greater than the E standard of the NAD+, so the NAD+ reaction gets reversed. Always, that's what we do. Under spontaneous conditions, these numbers tell us that's what happens. It gets reversed. So what we end up with is the following. Let's see. So we end up with acetaldehyde plus 2H plus 2 electrons goes to ethanol, and its standard is minus 0.197. And the other one gets reversed, so we write it as NADH goes to NAD plus H plus 2 electrons, and because we reversed it, we actually end up writing it as now a positive 0.320. We go ahead and we cancel electrons. In this case, there's 2 here and 2 here. We don't have to multiply by anything to balance it. We cancel this H plus with one of those H pluses, and what we're left with is the net reaction. Acetaldehyde reacts with this thing, NADH, under some slightly acidic conditions, and it turns into ethanol, and it releases NAD+. The net for this, just add this, and what you end up with is positive 0.123. That's all we've done. Aldehyde Aldehyde and ethanol, if you put them together with NAD plus and NADH, spontaneously what's going to happen is the aldehyde will react with the NADH, the aldehyde will reduce to ethanol, the NADH will become oxidized to NAD plus, and this is a measure of the extent to how fast it's going to go. Now that I have this, I can actually calculate the free energy change for this based on the equation that I've got. So now that I have this, my free energy change for this reaction is minus NFE of the reaction. It equals minus, well, N is the number of electrons that are transferred. We have 2 electrons that are transferred. Let me actually write here, 2 moles of electrons are transferred. We have 96,485 coulombs per mole of electrons. And of course we have the potential, which is positive 0.123 volts, which is a joule per coulomb. And I just wanted you to see that the units cancel. And when you multiply all this out, you get a delta G for this reaction is equal to minus 23,735 joules. There you go. That's it. That's all that's going on here. We have some species. We have a table of reduction potentials. We have some species. Its reduction potential is this. We have another set of species. Its reduction potential is this. Under conditions when these things are brought together, what is going to happen spontaneously? Well, spontaneously, because this is larger than this, it's going to reverse the other one to induce, it's going to flip it around. This will stay a reduction. This will become an oxidation. We go ahead and write it. We cancel electrons. We get the final balanced equation. So this is the reaction that's going to take place. It will. This reaction will take place spontaneously. Okay, we don't have to do anything. Doesn't mean the reverse reaction won't take place, because the reverse reaction does take place enzymatically. It can happen, but spontaneously this is what will happen, and this positive potential tells us that that will happen. This reaction as written, because of this equation, actually gives us the free energy change. Notice, minus 23.7 kilojoules. That's a very, very highly exergonic reaction. This reaction wants to go forward. That's all that's happening here. Okay, thank you for joining us here at Educator.com. We will continue our discussion of oxidation reduction chemistry in the next lesson. Take care. Bye-bye.